All right. In the previous video, we were talking about the fundamental theorem of invertible matrices, and we have added, I would say, eight more statements here. And once again, it is a kind of chain of facts. And if one is true, everything is true. And the one is false, everything is false. If I just know that one of them is true, like, for example, let's say the rank of A is equal to N. Now from here we can draw all of these conclusions. So what are these? Number one, if rank of A is equal to N, then A is invertible, and AX equals B has a unique solution for every B in Rn, and AX equals 0 has only the trivial solution. The reduced row echelon form of A is In, as A is a product of elementary row matrices, nullity of A is equal to 0, and the blah, blah, blah. If you just know one of these facts, now immediately we can just take all of these facts as granted because they are all true. So let's see one more example using these facts. Here, show that the following vectors form a basis for R3. Right? Now we know that from the definition to show that it forms a basis, actually we have two properties, right? Actually, we have to show that both properties hold. Number one is actually they should span R3. Number two is they must be linearly independent. But now using the fundamental theorem of invertible matrices, actually if I just know that the rank of this matrix that is formed by these columns is equal to 3, right? So now we don't have to go through all of these steps because using the fundamental theorem, it says that since the rank of A is equal to N, right? That means that it spans R3 here. So now immediately if you just reduce this to row echelon form, we don't have to reduce this to reduced row echelon form. We are not solving a system again, we're just trying to find the rank of A. So as you see here, 1, -1, 4, and here we will get this matrix, and as you see here, I cannot create 0 here, right? That means that all rows here, that is, the vectors in the rows of this matrix, they are linearly independent. That means that it shows that then the rank of A is equal to 3, right? The rank of A equals 3 means this actually, these columns, these column vectors, they span R3. And also they are linearly independent. That means that they form a basis for R3. So we have another important theorem here. Let A be M by N matrix. Then the rank of A transpose A is equal to rank of A. So we'll do some brainstorming here, and by proving this, you're getting more used to, or getting more familiar with the language of mathematics or linear algebra. And the second one, it says that the n by n matrix A transpose A is invertible if and only if rank of A equals n. Okay, so let's start with the first one. Okay, to prove this one, again, we know that we are talking about m by n, right? What is A transpose? That is n by m, and this A is m by n. So A transpose A is n by n matrix, and also this A is m by n matrix. So I'm just going to use, again, this theorem. We know that the rank of A plus nullity of A, that is equal to n. And also, actually, I can just write this for this matrix. If you just multiply this, we get n by n matrix. And also the similarly, so here I can just write here rank of, are we recording? Yes, okay. Rank of here, rank of A transpose A plus nullity of A transpose, okay, nullity of A transpose A, that is equal to n. It's also just single matrix. How am I going to prove that? Here, using this theorem, I'm going to show that actually this nullity of A is equal to nullity of A transpose A. Okay, so to show this one, here I'll just use this idea. Let me change name. Let's see, use blue. Okay. So let's see, we are talking about two sets. You can just so two sets. Let's say this one is S1, that is null space of A, and this one is, let's say, S2, null space of A transpose A. Okay. So now nullity of A equals nullity of A transpose A. That means that these two sets, S1 and S2, they have exactly the same number of vectors and exactly the same vectors. Right? Now I have to show that this S1 is equal to S2. And all of the elements, they are the same. And to show this, mathematically, how can I show this? I will show that if you just pick any element from S1, I will show that actually at the same time also it is the element of S2. And also if you just pick any element from, let's say, Y from S2, I will show that also it is the element of S1. And if I show this, actually this forces that then S1 must be equal to S2. That means that nullity of A is equal to nullity of A transpose A. Right? Because if you just pick anything from here, that thing exists here. And also if you just pick anything here, that thing exists here. What does it mean? It means that these two sets are exactly the same. Okay, so since A transpose A is n by n, it has the same number of columns as A. So now we are going to show that actual rank of A is equal to rank of A transpose A. So let's just start with the first one. Okay, how to show this? Now, I'll just start from the first one. Okay, so let me just take any x from S1. So now I have to show that also actually that x is the element of S2. Okay, I have to show that. I'm not sure. So every element from S, what does it mean? It means that that thing from S1, that is the solution of the system, that AX is equal to B. Guys, now you know that from the context, it's clear that A is a matrix, X is, what is it, n by 1 vector, and also B is n by 1 vector, because every time just writing bar, it's not convenient. Okay, from the context, you should understand that these are vectors, and this A is a matrix. It's not a real number. Okay, now that means that every x, if you substitute here, it specifies this. Actually, it's not B here, it is 0 vector. Okay, we're talking about homogeneous system, right? Null space. Okay, so actually here equal sign means, actually maybe I can write here 3 bars. It means that they are identical equal. If you just substitute here and multiplies by matrix A, it produces 0 vector, right? It's a solution. We are not solving the system here. Now, also I have to show here that, and also if I substitute this into this system, A transpose A, X will be equal to 0. I have to show this. To show this one, let me just multiply both sides by here, A transpose A, right? Okay, so if I just multiply both sides by A transpose, here we have A transpose A, X, and here we have A transpose and 0 vector. And A transpose 0 vector is just equal to 0 vector. From here, we can get that A transpose A and also this X, that is equal to 0. What does it mean? That means that also this X is the solution of this homogeneous system. That means that also that X belongs to S2. So that is the first step. Now the second one, I will show that if you just pick any vector from S2, I have to show that actually also that vector exists in AS1, and also it is the element of S1. So picking any vector from S2, what does it mean? It is the solution of the system, that is A transpose A, X, that's equal to, identity equal to 0, right? So I have to show that also actually satisfies that equation AX equals 0. To show this one, let me just multiply both sides by X transpose. What do we get here? Do we have X transpose, A transpose, and AX, and here we have X transpose, and here we have zero vector. So now, by using the property of transpose, this X transpose, A transpose, I can just write it as AX transpose. And here we have AX, that's equal to, on the right hand side, we have 0. And I'm just going to use this property, if you remember, changing matrix multiplication into dot product, right? Let me open, where am I? Open a small window here. And if you remember, here we have two vectors, U transpose V is just equal to U dot V, right? And also here we have two vectors, right? AX transpose, that means that if it is, what is it? If it is a column vector, this AX transpose becomes a row vector. So again, using this, I can just change this matrix multiplication into dot product. So that one becomes then AX dot AX. On the right hand side, we have 0. And also, if you remember, U dot U is equal to 0 if and only if U is equal to 0. Otherwise, U dot U is never equal to 0. So from here, we have something, and dot product something is equal to 0. That means that this AX must be 0 vector. Otherwise, the dot product of itself is never equal to 0. So that means that also X is the solution of this AX equals 0, this homogeneous system. And this implies that also X is the element of S1. So that shows that then S1 is equal to S2, or null space of A is equal to, I mean, it's the same as the null space of A transpose A. What does it mean? It means that nullity of A is equal to nullity of A transpose A. So that means that if these two things are equal, that forces that rank of A must be equal to rank of A transpose A. How about part B? Part B is the n by n matrix A transpose A is invertible if and only if rank of A equals n. We're just using a fundamental theorem, right? And we know that the n by n matrix A transpose A is invertible if and only if rank of A transpose A is equal to n. But A, actually, this is if and only if rank of A is equal to n, right? Because if one is true, another one is true. Otherwise, both are not true. They are actually making each true facts. Okay. So now we will talk about the last section of this subchapter, that is subspaces, basis, and dimension. That is the coordinates. So, and after that, I'll finish the class. We have two examples. We now return to one of the questions posed at the very beginning of this section. How should we view vectors in R3 that live in a plane through the origin? Are they two-dimensional or three-dimensional? The notions of basis and dimension will help clarify things. A plane through the origin is a two-dimensional subspace of R3 with any set of two direction vectors serving as a basis. Basis vectors locate coordinate axes in the plane subspace, in turn allowing us to view the plane as a copy of R2. Before we illustrate this approach, we prove a theorem guaranteeing that coordinates that arise in this way are unique. Anyway, here we will talk about the definition of coordinates. Let me just say coordinates, actually what we mean by that. Anyway, before giving the definition, let's prove this theorem to make sure that there's a unique way of describing a vector using the basis vectors. So it says that let S be a subspace of Rn, and let B, who actually the vectors are V1, contains these vectors V1, V2, Vk, be a basis for S. For every vector V in S, there is exactly, that's important, there's exactly one way, that means a unique way, to write V as a linear combination of the basis vectors in B. Okay. So if you're talking about, again, that's Rn, 10-dimensional space, and we are talking about some subspace S, and also we know that it is basis are this, actually this B, whose which contains these vectors v1, v2, vk. And you may think that in how many different ways we can write if you just pick any vector from S as a linear combination of these vectors v1, v2, vk. And this theorem is saying that it is only one way, unique way. You cannot actually show this in the second different way. So to show that, actually, let's assume that in two different ways, I can write this V as a linear combination of this V1, V2, Vk. That is the first way. And here, I cannot see my laser pointer. Okay. Okay. So here, this one, the first way, assume that I can just write this V as a linear combination of V1, V2, Vk using these coefficients C1, C2, Ck. And also I'm saying, assuming that also we have another way. The second way also I can write this V in a different way as a linear combination of these vectors, D1 times V1 plus D2 times V2 plus Dk times Vk. So I will show that actually if this C1, D1, C2, D2, they are exactly the same numbers. Since actually they are representing the same vector, right? Left-hand side, that's V, and also V at V. That means that also right-hand sides must be equal to each other. That means that the left-hand side, C1, V1 plus C2, V2 plus CK, VK, it should be equal to D1, V1 plus D2, V2 plus dot dot DK, VK. And if you just take everything to the left-hand side and simplify this, what do we get here? Here we have take this to this side, v1, it's a common vector, so just take this out, c1 minus d1, v2, d2, I mean v2 here, c2 minus d2, here we have c2, d2, and dot dot, here we have ck minus dk times vk, equal on the right hand side, we have zero vector, right? And now we know that actually since this B forms a basis for the subspace S, right? And these vectors are linearly independent. They must be linearly independent, otherwise they cannot form a basis. That is the first property of being a basis. So since this V1, V2, Vk, these are linearly independent vectors, right? And this forces that actually all of these coefficients must be equal to zero. That's the definition of linearly independence. So that means that C1 minus D1 and C2 minus D2, all of these coefficients, Ck minus Dk, they must be equal to zero. Now from here, of course, we get that C1 must be D1 and C2 must be equal to D2 and Ck must be equal to Dk. That means that there is the only one way to describe a given vector as a linear combination of these basis vectors. So since it's a unique way, so now we are going to attach a special name to this, which is called coordinates. So let S be a subspace of Rn, and let B contains this, which contains this vectors v1, v2, vk, be a basis for S. Let V be a vector in S and write V as a linear combination of this C1, V1 plus C2, V2 plus dot dot CK, VK. Then C1, C2, dot 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 CK are called the coordinates of V with respect to B, the basis B. And the column vector, just using this notation, is called the coordinate vector of V, with respect to basis B. Okay, that is how we define the coordinates of coordinate vector of given vector with respect to given basis. Okay, now I need pen. So let's epsilon contains these vectors e1, e2, e3. These are standard unit vectors. Be standard basis for R3. Find the coordinate vector of V with respect to epsilon. So that means that we know that actually I can just write this V, right? This V is equal to 2 times 1, 0, 0 plus 3 times 0, 1, 0 and plus 8 times 0, 0, 1, which is 2 times E1 plus 3 times E2 plus 8 times E3. Then coordinate vector of V with respect to the given basis, that is coordinate vector of V with respect to the given basis is, what is it? Just the coefficients of these vectors, that is 2, 3, and 8 itself, right? Okay. Another example, let's U 3 minus 1, 5, and V 2, 1, 3, and W 0 minus 5, 1, B, 3 vectors in the same subspace S of R3. But so we don't know actually, are they dependent or independent? Find the coordinate vector of W with respect to this basis. So since this U and V are not parallel to each other, right? And they form actually a basis for, what is it actually? It's just a plane passing through the origin. To do this one, we know that actually first when you just write this next to each other, form a matrix. And if you just reduce this to reduced row echelon form, from here we have two leading ones, right? And that means that actually one vector is dependent on other vectors. And also actually when we just reduce this to reduced row echelon form by using some elementary row operations, we know that the columns of this matrix and columns of this matrix, they have the same linearly dependence relationships. That means that what I can see here, as you see here, if I multiply the first column by 2, the second column by -3, I can get the third column. That means that the first column is U. That means that the W is equal to 2 times U minus 3 times V. If you check this, we have 2 times 3 minus 3 times 2, that's equal to 0. 2 times -1 minus 3 times 1, that's equal to -5. And 2 times 5 minus 3 times 3, that's equal to 1, right? So now, since U and V, actually, they are serving as a basis vectors, and here the coefficients are 2 and 3. Now I can write here, coordinate vector of W with respect to B. So coordinate vector of W with respect to this B is equal to, what is it? 2 and -3, right? What does it mean? It means that here in this picture, as you see here, this one is vector W, and here this one is vector U and vector V, and you're allowed to move only in this direction, in the direction of V, and in the direction of U. And the question is, how can I reach actually the terminal point of this W at this point if we are allowed to move only along in these two directions? And here it's saying that along U, you have to move 2 units, right? Here we have U, actually 2 units. And after that, in the direction of V, this is the opposite direction, 3 units, right? If you just move 3 units in the opposite direction, you will reach the tip of this W. That is actually what this coordinates mean. And this is our last example for today. And tomorrow we'll talk about linear transformation. So let's U and V and W act a similar example, just different numbers. Again, these 3 vectors in the same subspace S of R3. Find the coordinate vector of W with respect to B. So again, that is our matrix. If you just reduce this to reduced row echelon form, we will get this thing. From here, you can see that 3 times the first column, that is U, minus 2 times the second column, it is V. It gives us W. So the coordinate vector of W with respect to the given basis is, what is it? It is 3, -2. Okay, that's all about subspaces, basis, dimension, rank. And here we have one quote, and I will finish the class. People will throw a stone at you, don't throw them back. Collect them all and build an empire. It's a very powerful quote. Guys, thank you very much. If you have any questions, you can just contact me through Telegram, okay? Or if you have any question that you're trying or struggling with, and also you can just let me know. I can make a video and share with you. That's enough for today. And as you know, you have midterm on Friday, and I hope you are preparing for that. Maybe I'll give you more details about midterm tomorrow. Thank you very much. See you tomorrow. Bye bye.